All right, everybody. So title your notebook 3-4 warm-up, and what I'd like you to do is to maybe pause this video and for you to try these two inequalities. We did these the other day, so you should be able to solve them coming up with your solution sets. So the first thing I like to do is to isolate the absolute value in the inequalities, so I wind up getting the x plus 1 is less than 2. Remember, we have two scenarios. So I have x plus 1 is less than 2, and negative x plus 1 is less than 2. Well, this one's easy to solve, so that's just x is less than 1. And this one, I'm going to choose to do something different than I did in the other video. I'm going to divide by the negative 1, which switches the direction of the sign. And that's actually the step that a lot of teachers teach people in Algebra 2, just to rewrite it twice and then switch the sign and make the other number negative. But, you don't really know why that's happening. So there we go. We have x is less than 1 and x is greater than negative 3. So we can write that as a compound inequality, or we can write it on the number line. Oops, negative 3. These are open circles, and we want less than 1 but greater than negative 3. And actually, we can write it as a interval for interval notation. So either one of these three methods of expressing your solution are going to be good. I might ask for at least two of them, including the number line. All right, I'm going to try my second one here. And again, isolating the inequality or the absolute value first is what I like to do. And so that's greater than or equal to 16. Divide both sides by 2. And then so here's my two scenarios where underneath of the radical could have stayed positive and underneath of the radical could have been negative. Radical. What am I saying? Radical. Absolute value. Mr. Godek. All right, so now my next one is I'm going to solve this. Subtract 8 from both sides. And again, I'm going to divide both sides by negative 1, which switches the direction of the inequality. Still stays equal to. And then subtract 8, so x is less than or equal to negative 16. So look at this. This is interesting. So we get values that are greater than 0 or equal to 0, or values that are less than or equal to negative 16. So we get those. And if we wrote it as an inequality, I mean, we could still write it as a compound inequality. So we'd have negative 16 is greater than or equal to x is greater than or equal to 0. A little backwards from how we normally write it. And the last way, I'll squeeze this in here, is you can write them in interval notation. So we're going to go all the way from negative infinity up to negative 16, not inclusive. Oops, nope, that's not true. I am including 16, so brackets, unioned with 0 all the way up to infinity. So a couple different ways that we can express that. Okay, so let's get into today's review. So we're going to talk about inverses, inverse functions, and inverse relations. So questions we should be able to answer by the end of this is, what does it mean that two equations are inverses of each other? How do you create inverse equations? And how can you tell if two equations are inverses of each other? How are their graphs related? And how can you tell if the inverse of an equation will be a function or not? This is all Algebra 2 related stuff. I'll come back and repeat this slide at the end, and maybe we'll see what we can answer. So let's title our notes 3-4 Inverse Functions and Relations. Give that a title up there. And again, the basic question is, how do we determine and graph inverse functions or inverse relations? So make sure you get that title down. An inverse relation is And if you remember about inverses, the big thing about inverses is switching those x's and y values. So inverse relations is where one of them contains a point BA and the other one contains the point AB. We're just switching all the x's and the y values. So switch x and y. So all the x and y values get switched, and that new graph would then be the inverse. So down here, my examples with the red and blue graphs. The red graph, if you take every coordinate on the red graph and switch the x and y coordinates, you would get the blue graph. And if we remember also from before, inverse functions, their graphs are symmetric around the line y equals x. And if you think about it, why is that? That's acting like an axis of symmetry. Well, because every single point on the line y equals x is its own inverse. So if I take any points on this line, 1, 1, 2, 2, 3, 3, 4, 4, and switch the coordinates around, you get the same equation back. So y equals x is the axis of symmetry, and we can reflect across that line and get my two graphs. And same thing here. Red graph will reflect across to get the blue, and same thing here. Now we could do it with little individual points, which we'll take a look at. But here at least is the graph. So I would make sure that I'm jotting down that inverse graphs are symmetric around the line y equals x. Remember, as always, you can pause if I'm going too fast. So let's examine one here. So let's graph x squared minus 2 by making a table of x and y values. So y equals x squared minus 2, and I'm only going to do it between -2 and 2 and just the integers. So x and y. So I'm going to go from -2 to -1, 0, 1, and 2. And we're just going to substitute values in. So -2 squared, that's going to be positive 4 minus 2 is 2. -1 squared is going to be 1, minus 2 is -1. 0 squared minus 2, that's -2. 1 squared minus 2, that's -1. And 2 squared minus 2 is 2. And if we plot those points, just make yourself a little coordinate axes. So -2, 2, -1, 1, 0, -2, and 1. Oops, this point was wrong. Let's see if I can get my eraser here. It was the point -1, -1. There's my point. And there's 1, -1, and then back up to 2, 2. And hopefully you know this is just simply a parabola that's been shifted down 2 units. We know that from all of our transformations that we did before. So now what I want to do is I want to make a new table by switching every x and y value. So I'm going to make a new table, and I'm going to switch all the x's and the y's. So -2, -1, 0, 1, 2 is now y values, and 2, -1, -2, -1, and 2 are x values. So let's plot those points. So 2, -2, oops, I'm missing these. Can't plot my points well. So hopefully you're doing a better job at plotting your points. So -1, 1, -2, 0, -1, 1, and 2, 2. And if we look carefully here and plot those points, there is that graph. And if we look carefully, we can put a diagonal line of y equals x, the axis of symmetry, and indeed these graphs are reflections of each other across that line. So is this red line a function? I don't think so. Let me get another color in here. Remember, to be a function, it needs to pass the vertical line test. And the vertical line test, this fails. So it is not a function. Well, could I tell that from the original function? Well, yeah, if I did a horizontal line test on the original one, because I switched all the x's and the y's, and now horizontal line test became the vertical line test, and the horizontal line test fails, which means the vertical line test will fail. And we'll mention that here in a second. The bigger question is, what's this new equation? what's the new equation that we created by switching the x's and the y's? Well, we can do that by literally taking the original equation and switch the x's and the y's. So x equals y squared. Now that technically right there is the inverse. It's an inverse relation. It turns out not to be a function, but it's not solved for y. So I want to solve for y. So y squared equals x plus 2. And then y is going to equal the square root of x plus 2. But remember, we got to do a plus or minus. Remember when you take square roots? Because you got to count for the positives and the negatives. So that is actually the equation. You can't squeeze it in there. It's plus or minus the square root of x plus 2. That is the inverse relation of my original parabola function. Hopefully all of this kind of seems familiar. If I went too fast, you can always back up and repeat screens ago. The original function did not pass a horizontal line test, so therefore the inverse will not pass a vertical line test and will not be a function. So let's find the inverse of each of these and solve for y. So we're just going to practice writing them. So here's my original line, and if I'm going to switch the x's and the y's. Now that technically is the inverse right now. It's just not solved for y. So I just need to 2y, and then I would subtract the 3 over. Hopefully what I just did there doesn't throw people off. Switch the equation around, and I'm going to divide all the terms by 2. So 1/2 and 3/2. There is my inverse. And it actually is a function. Linear functions are functions. And then my second one, again, you can pause it and try it yourself. That, again, is already the inverse, but it's not solved the way I like to solve it. So x minus 1. I'd like to get y's by itself. And once again, we're square rooting, so I need the plus and the minus. So pretty simple to actually write an inverse and solve for y. It's not a big deal. Screen here. So vertical line. So, and we said before, two relations are considered inverses if I've got a point A, B on one of them and BA on the other one. And as I said before, the horizontal line test tests if the inverse will be a function. So I can perform a horizontal line test on my original function. So let's pretend that this blue line over here on the left, that's my original function. Well, since it passes the horizontal line test, the inverse function would pass a vertical line test. So this passes, so the inverse is a function. I'm not graphing it, but I know that the inverse will be a function. The original function here is a parabola, and it fails the horizontal line test, so the inverse will not be a function. And I can tell that if I go back to tests for functions, horizontal line test tests if the inverse of that graph will be a function or not. And again, hopefully this is some Algebra 2 review. So let's think about this graph. All right, so what is this graph? Well, we should know what this graph is. So this is just a parabola, shifted 3 to the left and 5 down. So it looks something like this. Now we can probably, I'm going to do a little better job here. And if I think about what the y-intercept is going to be of this parabola, because I might need to show a little bit of the width, if I take this and expand it, x squared plus 6x plus 9 minus 5, I can see that x squared plus 6x minus 4, plus 4. So again, I'm going to go and plot my, there is 3 to the left and 5 down, and I know I'm going to pass up at positive 4. So I'm going to come down and look something like that. Ooh, hopefully yours is a little smoother. So I just graphed f of x, and let's label it because Labels are important because there's going to be more than one graph graphed. So the first question, is the inverse of this function going to be a function? Well, how do we test for that? Well, we do a horizontal line test, and since the horizontal line test hits twice, the answer is going to be no, because it fails the horizontal line test. So now I want to find the inverse. So if this might be the first time we're seeing this, this is the inverse notation, f to the negative first, that's telling me an inverse. And so I just have to switch my x's and y's. Now I don't see a y up here, but I know y is the same thing as f of x. So x plus 3 squared minus 5. So I'm going to switch the x and the y. And again, this technically is the inverse, but it's not written explicitly. So I'm going to have to add the 5 over square root both sides, which causes a plus or minus. And then, so in the end, I'm going to get negative 3 plus or minus, if I subtract that 3 over x plus 5. Or maybe written a little bit easier from what we had done in the past, I'm going to put the minus 3 on the end. So what does this look like? Well, it's the square root function. We know what that parent function looks like. So it's going to shift 5 to the left, 1, 2, 3, 4, 5, and then down 3, 1, 2, 3. So from here, I know I'm going to have a graph, a positive and a negative. So positive and a negative coming down through here. And so then I get a sketch of my inverse function, which I will call f to the negative first. Now let me clean this up a little bit because this actually doesn't look like it should if I think about it, and that's one of the reasons why I made this point. So definitely this coordinate is right. But if I have a point 0, 4 on my original graph, I'm going to have a point 4, 0 on my new graph. So I will now know that I'm going to go like this instead. And now I should start to see the axis of symmetry come right through there of y equals x. So if you even look at this coordinate right here, I'm going to make them black. So this was the coordinate negative 3, negative 5. That was on my original function, and the point negative 5, negative 3 is on my inverse. So it even shows the inverse as that at that coordinate. All right. So cubed root function. We might need our calculator for this because I haven't done this before. So let's actually graph this original function to begin with. So in your calculator, if you go to y equals, you want to go to the math menu, and then you'll see the cubed root function. We did not do this as a parent function yet. So let's just kind of see what this looks like. Now, hopefully we would know this is a shift of 1 to the left. So it's got this graph that looks something like this. And it's going to hit there at 0, 1. So that's my function. So now what's the inverse look like? So I'm going to switch. My original function is the cube root of x plus 1. And so I'm going to switch my x's and y's. Now how do I get rid of a cubed root? What is the inverse of cube rooting something? It is cubing something. And yes, I did say inverse on purpose here. We're dealing with inverse relationships. So the cube and the cube root cancel each other out, and I get x cubed minus 1. Well, hey, that's a function that I know. X cubed minus 1, let me switch colors here for my inverse. Well, that's the cubic function just shifted down 1. So it's going to be coming through like this. And actually I should be showing that these graphs, when I clean my graph up, I think I made a slight mistake. That's why we should be using erasers here. I'm going to clean this one up. So the original function, if I substitute in 0 into the original function, I'm going to get 0, 1. So I should be going like this. And so in the inverse, I'm going to be getting the 0.10. So first of all, it's shifted down 1. That was this shift down 1. And then like that. And again, it's a nice little check in the end if you draw your axes of symmetry coming right through. And look, they hit right at that 0.22. And I should also label my inverse function graph f to the negative first of x. All right, hopefully some of this is seeming familiar. The last thing we're going to do is talk about testing inverse functions. And two functions, f of x and g of x, are inverses if their composition, when you substitute one equation into the other, if everything cancels out and you just get x. So you want to pause this and jot down what's in the yellow box into your notes. And let's look at this example here. So I've got two equations. I'd like to know if they're inverses. Now I could literally take the first equation, plot all of its points, and see if the points flip around, the x's and y's flip to become y equals y and x's, to give me that. But it's an infinite number of points that I would have to test. I could look at the graph, but the graph isn't for sure. It gives me a general idea. You even saw that I was kind of shaky in some of my graphs if I didn't think about what was going on. But let's do compositions of functions. Let's call this first one f of x and this one g of x. Now if you remember, composition of functions, f of g of x, that means the g of x function is being substituted into the f of x function. It's like it's eating it. It's inside of its belly. So f of g of x. So where do we start with math? We start on the inside and work our way out. So f, and then I'm going to write in the function g of x. And g of x I'm using is 1/2 x minus 1. So now what do I do with 1/2 x minus 1? Well, it goes into the f of x equation. If I asked you what's f of 0 is, well, that would be 2 times 0 plus 1. If I asked you f of 1, I would say 2 times 1 plus 1. Well, I'm just asking f of 1/2 x minus 1. So it's going to be 2 times 1/2 x minus 1 plus 1. So it's the f function, but inside, I'll show this in blue, this equation right here is substituting right in for the x. It feels weird because you're substituting an x with an expression with an x. Now the thing I want to do is I want to simplify this and see what's going on. So I got 2 times 1/2 of x, well that's just going to be x. And then I have 2 times -1, so that's plus -2 plus 1, and I get x minus 1. Well, right there, since I didn't get x, I know that these are not inverses. So that was a little bit quicker than trying to graph them and look at the graphs, or obviously looking at an infinite number of points, which would have taken forever. Okay, one last one. How about I pause here and I let you find the inverse and then graph both of them. So I'm going to graph each. So 1/2, I'm going to start with the first one, 1/2 x minus 2. Just plotting some points. And make sure to label it. Oh, it looks like I'm graphing the inverse first. So the first one I had listed. And then the second one, which was the original function 2x plus 4, 1, 2, 3, 4, and a slope of 2 up 2 over 1. Now I'm plotting points. Oh, that point happened to hit the other one. Oh, this one's on the other line. What coordinate is that? That's the coordinate -4, -4. Huh. If you switch -4, -4, the x and the y, you got -4, -4. It is on both graphs. Any point that would fall on the line or the axis of symmetry of y equals x, that coordinate would be on both graphs. And it looks really nice. This is symmetric across that line. Those two are inverses of each other. Now, why do we care about inverses? Well, big important inverse functions are going to be coming up in trigonometry, and they are going to be lifesavers for us in what we do. So recap here. So maybe if you want to pause the video real quick here and then just jot down just some answers to these questions before I talk through them real quick here. Right, what does it mean that two equations are inverses of each other? So we can basically say that each x and y value on function becomes yx values on the inverse. Basically, we're just switching the x's and the y's. How do you create an inverse equation? Well, you just switch the x and the y's. How can you tell if two equations are inverses of each other? Well, we can do our compositions. F of g of x must be equal to x, and g of f of x must also be equal to x. How are inverse graphs related? Well, they're symmetric across the line y equals x, the axis of symmetry for inverse functions. And how can you tell if inverses of an equation will be a function or not? You can use a horizontal line test on the original function to see if its inverse is going to be a function or not, or whether or not it'll pass the vertical line test. All right, there you go. Make sure you check the Canvas page to see what the assignment is.